On March 9, 2016, in a conference room at the Four Seasons Hotel in Seoul, a computer program played its 37th move of Game 2 against Lee Sedol, at the time the most decorated active Go player alive. The move landed on the fifth line of the board, a fifth-line shoulder hit, played early against a world champion in a region no professional occupies at that stage of the game. The commentators went silent. In the documentary filmed during the match, Fan Hui, the European Go champion who had played AlphaGo privately 5 months earlier and lost every single game, was watching from the audience. He looked at the stone on the board. His hands started trembling. Lee Sedol was on a smoke break when the move was played. He came back to the table, saw it, and sat in silence for 12 minutes before he could respond.
To understand why 12 minutes matters, why a man who has read Go boards at a glance since he turned professional at 12 needs 12 minutes just to begin forming a reply, you have to understand what Go was supposed to represent. Chess fell to computers in 1997. Deep Blue beat Kasparov, and the world processed it and moved on. Go was different. The board is 19 by 19. The number of possible game positions exceeds the number of atoms in the observable universe by a factor that makes that comparison almost meaningless. Researchers have described it as if every atom in the observable universe were itself a universe, and you counted every atom in all of those, you'd be getting closer. What this means practically is that brute force calculation, the approach that worked for chess, simply doesn't scale. You can't enumerate your way through Go. The way human experts play involves something that looks less like calculation and more like aesthetic judgment. You feel where the stones belong. The Go community's consensus was clear. Computer supremacy was decades away, if it was possible at all. Go was the last fortress, the proof that human intuition was still sovereign over any machine.
Move 37 was a fifth-line shoulder hit in a position where conventional Go wisdom says you don't play on the fifth line that early. The commentators dismissed it immediately as a mistake. It took Lee 12 minutes to respond, and his eventual response was itself praised as one of the strongest moves in the match. AlphaGo won the game anyway. It won the series 4-1. The program had trained on 30 million positions from human games, then improved by playing itself millions of times more through reinforcement learning. No human teacher, just the outcome of each game as signal. The result was indistinguishable from creative judgment. Fan Hui, watching Move 37 land on the board from the audience, described it later as feeling like something from another world.
There's a second moment from that match that gets less attention than Move 37, but matters just as much for what comes next. Game 4. Lee Sedol played his own impossible move, Move 78, a wedge in the center of the board. AlphaGo's evaluation function had assigned that specific move a probability of 1 in 10,000, the odds that any human would find it. The algorithm had deemed certain sequences irrelevant and simply hadn't evaluated them. Move 78 drove straight through that gap. AlphaGo's confidence reportedly plummeted from near certainty to something approaching random thrashing. It didn't understand what had happened to it. The audience erupted. Lee Sedol won Game 4. It remains the only recorded game AlphaGo ever lost to a human being in a formal match.
Which means the same match, the same week, produced both of those things. A machine that played a move so original that a world champion needed 12 minutes just to process it, and a machine that completely collapsed when a human found the one crack in its search process, the sequences it had simply decided to ignore. Both of those facts are true, and both of them will matter for everything that comes after this.
To understand how AlphaGo existed at all, you have to go back 2 years. January 26, 2014. Google announced it had acquired a London-based artificial intelligence company called DeepMind for approximately £400 million, roughly $650 million at the exchange rate of the time.
And the thing you notice immediately when you look at what Google actually bought, DeepMind had no product, no revenue, no commercial application. What it had was roughly 75 people, about 30 of them PhDs specifically in deep learning, and a research agenda built around one central idea. You can train a system not by showing it correct answers labeled, but by rewarding it for good outcomes and letting it discover the rest. Reinforcement learning. Give the machine the rules and the score. Let it figure out how to win.
Their most notable published work at the time of the acquisition was a neural network that had taught itself to play Atari 2600 Breakout without anyone telling it the rules. You gave it the screen pixels and the score. That was the entirety of the input. Everything else it derived through play, through millions of iterations of trying things and observing what happened. The system started with nothing, playing randomly, and ended up discovering strategies that expert human players used without ever having been told those strategies existed. DeepMind hadn't solved anything commercially, but what they demonstrated was a different kind of machine, one that learns from interaction rather than instruction.
And DeepMind had Demis Hassabis, chess prodigy, rated 2300 by age 13, then a game designer, building the kind of complex simulations systems that required him to think carefully about how agents learn and adapt inside environments. Then a neuroscience PhD at University College London, studying the structures in the brain that support memory and imagination. The combination of competitive gaming intuition, systems design, and cognitive neuroscience in a single founder was unusual enough that when DeepMind went to market, multiple major technology companies wanted it. Mark Zuckerberg reportedly flew to London personally to make a pitch. Hassabis chose Google.
But he chose Google with conditions. Before signing the acquisition agreement, Hassabis insisted that Google establish an independent ethics board with authority over how DeepMind's AI research would be used. This was reported at the time by The Information that DeepMind required the board's establishment as a precondition of the deal. Google agreed. The board was announced. Its membership was never disclosed publicly. By 2019, reporting by multiple outlets indicated the board had either never properly convened or had been quietly dissolved. The governance structure that was the stated price of the acquisition had vanished.
It's worth pausing on what Hassabis was actually asking for, because it wasn't vague. He wasn't asking for a commitment to responsible development in the abstract. He was asking for a named board with real authority over deployment decisions, a structural check, not a philosophical one. That's specific. That's the kind of demand that signals genuine concern rather than PR positioning. And the fact that it disappeared, membership never disclosed, existence apparently ended within 5 years, tells you something durable about the lifespan of safety commitments made during acquisitions. The commitment got the deal done. The deal closed. The commitment dissolved.
The cultural impact of the AlphaGo match did not fall evenly. In the United States and Europe, it registered as a significant AI milestone. Serious coverage, genuine interest, processed as an important data point. In East Asia, it was something else entirely. The match was broadcast live on national television in South Korea. Go holds a weight in Korean culture that has no obvious Western equivalent. It is woven into education, into professional aspiration, into national identity in ways that chess never quite achieved anywhere. An estimated 60 million people in China watched portions of the coverage. After the series ended, the Korean Baduk Association awarded AlphaGo an honorary 9th Dan ranking, the highest level of professional certification in the sport, the designation reserved for the greatest players alive. A computer program received that designation.
And Lee Sedol retired at 36. He had started playing professionally at 12. He had won 18 international titles. He had beaten AlphaGo in Game 4 with a move the algorithm never even considered. And in 2019, he announced he was leaving professional Go. He told reporters that even if he became the world's #1 player, there existed an entity he could not defeat. He was the only human ever to beat AlphaGo in a formal match. He chose to stop playing.
The earlier version of AlphaGo that beat Lee Sedol was not, it turned out, the end point. In late 2016, an updated version played 60 games against top professionals online under the pseudonyms Magister and Master, playing on Korean and Chinese Go servers where the identity of the opponent wasn't revealed until after the games. It won all 60. Then, in October 2017, DeepMind published AlphaGo Zero, entirely different approach. AlphaGo Zero trained through pure self-play. It never saw a single game played by a human being, not one position from the 30 million human games that had been the foundation of the original AlphaGo. Within 3 days of training, it had already defeated the version of AlphaGo that beat Lee Sedol. Within 40 days, it surpassed every previous version of AlphaGo ever built. A system that learned Go entirely on its own, against itself, with no human input, became the strongest Go player in recorded history in less than 6 weeks. The question of whether human expertise was even a useful starting point now had a data point. 18 months after AlphaGo defeated Lee Sedol, a team of 8 researchers at Google Brain published a paper, June 12, 2017. The title was Attention is All You Need. It introduced what they called the attention architecture. The authors were Ashish Vaswani, Noam Shazir, Nikki Parmar, Jakob Uskareit, Ilian Jones, Aidan Gomez, Lukasz Kaiser, and Ilya Polosichin. They were listed as equal contributors. The author order was randomized, a deliberate choice to ensure that no one name would be read as the originator above the others.
To understand what they built, I need to back up and explain what existed before it, because the transformer is defined against its predecessors, and if you don't know the predecessors, the improvement sounds abstract. Before 2017, if you wanted a neural network to process a sequence, a sentence, a paragraph, a line of code, there were 2 dominant approaches. Recurrent networks processed sequences one element at a time, carrying a running summary forward. Word by word, frame by frame, the network accumulated context. The problem was that context degraded. By the time you reached the end of a long passage, the memory of the beginning had faded. Mathematically, it's because the signal gets diluted as it passes through more and more layers. Recurrent networks read a document the way you would if you were only allowed to see one word at a time, had to hold your notes in your head, and had to discard earlier notes as you went. A convolutional network reads it like you're using a magnifying glass, seeing local details clearly but missing the long-range connections. Useful for some things, still limited in how far any piece of information could travel across the sequence. And crucially, both approaches were sequential in a way that made them slow. You couldn't fully parallelize the computation because each step depended on the one before.
The transformer replaced both with a single mechanism, self-attention. The insight was that instead of processing a sequence one step at a time, you let every element attend to every other element simultaneously. And the network learns, through training, which relationships matter.
Every word in a sentence can look across the entire sentence and decide what's relevant to understanding it. Not just the words nearby, any word, anywhere. And because all of that happens in parallel, every position looking at every other position at the same time, you can use the full widths of modern hardware. The training time on standard machine translation benchmarks dropped from weeks to days. The results were better. The compute was a fraction.
The analogy I find most useful: a recurrent network reads text the way you would if you were only allowed to see one word at a time, had to hold your notes in your head, and had to discard earlier notes as you went. A convolutional network reads it like you're using a magnifying glass, seeing local details clearly but missing the long-range connections. Self-attention reads the whole thing at once and can ask, about any word or phrase anywhere in the document, what else here does this connect to? And answer that question for every element simultaneously. The quality of what you can learn from the same amount of data is fundamentally different.
The 2017 paper demonstrated the architecture on English to German and English to French translation, and the results were state-of-the-art on both tasks. But the transformer's real significance wouldn't be visible from the paper alone. The paper showed it could do machine translation well. It didn't show, couldn't yet show, what would happen when someone took the architecture and trained it to do something simpler and far more general: predict the next word on everything at enormous scale. That question wasn't asked inside Google. By the time it was asked, the people who built the transformer had already left.
And that's the part that should be impossible to overlook, but somehow keeps getting overlooked anyway. Attention is All You Need was not a front-page story. It was a conference paper, one of hundreds submitted to NeurIPS that year, the field's main venue, competing for attention alongside papers on image recognition, speech synthesis, reinforcement learning, robotics. The authors framed it modestly: a better way to do machine translation. That framing was accurate. It was also a complete understatement of what they'd built. The paradigm shift only became legible when someone else, outside Google, at a lab that hadn't existed when the paper was conceived, took the architecture and asked a different question entirely.
By 2025, Attention is All You Need had accumulated over 173,000 citations. The architecture underlies every major language model, every image generator, every code assistant developed in the decade that followed, and every one of the 8 people who wrote it had left Google before that significance fully registered. Noam Shazir co-founded Character.ai. Nikki Parmar and Ashish Vaswani co-founded Adept. Others dispersed across startups and rival labs. The paper was public, published, indexed, freely readable. The architecture belongs to anyone who understands it, but the team that built it was gone.
We named this pattern in Act 1. The organizations that fund the breakthroughs never keep the people who make them. Dartmouth brought the researchers together and they scattered to build the field at other institutions. Sci-Far kept Hinton's network alive through 2 winters, and Google hired Hinton, but not permanently and not everyone. Here it is again, at a different scale. Google built the architecture that would define the next decade of artificial intelligence. Google published it. Google lost every person who wrote it before anyone fully understood what they'd made. The architecture walked out the front door, not because anyone stole it, because it was a paper. Anyone could read it. Anyone could build with it. And the people who did weren't inside Google anymore.
By mid-2017, the pieces were all on the board.
Dartmouth, working inside Google's corporate structure, had shown that reinforcement learning could produce something indistinguishable from creative brilliance, and something that collapsed completely when confronted with a move it had decided not to consider. The transformer had solved the parallelization problem that had bottlenecked every previous architecture for processing language. And a small nonprofit lab in San Francisco, founded just 2 years earlier with pledges totaling $1 billion, had already begun working with the architecture Google had published. The baton was moving fast. The GPT era was about to begin. Next, on How AI Happened, the people who proved that scaling works walked out of OpenAI and started a safety company. Then they raised billions, outperformed GPT-4, and signed a $200 million contract with the Pentagon. Whether that's a contradiction or a conversion depends on when you think the lesson landed. I'm Knox. Every Saturday on Pulse Deep Dive, one story, the history, the present, and what comes next. Find it wherever you listen.
How AI Happened is produced by Singularity Pulse Network. This series is for informational and educational purposes only. Historical accounts are sourced from published research, reporting, and public record. Some timelines are condensed for narrative clarity. Nothing in this series constitutes legal, financial, or technical advice. Views expressed are those of the hosts and do not represent the positions of any organization mentioned. For sources and corrections, visit singularitypulse.network.